day everyone. Today we are going to have a look at some very beautiful models. Those are beautiful physically, extrinsically, and beautiful because of their properties, that is intrinsically. And they are Platonic solids or regular polyhedra. Now we already know what polyhedra are. Polyhedra are, as we know, solid figures bounded by plane faces and they're closed. Alright, now the question is that just as in case of polygons, it's a closed figure bounded by line segments. The next question that comes to us is, can we have regular polygons? Yes. How many number of sides? Any number that you like. 1000? Yes. How about regular polyhedra? That is a question that is to be understood and appreciated. But before that, we first try to find out what a regular polyhedra is. We keep comparing with polygons. We want everything to be congruent. So, we say that a polyhedron is regular if all its faces are regular polygons and congruent to each other. And secondly, at every vertex, the same number of faces should meet. For example, at this vertex there are 3, at this vertex there are 3, at this vertex there are 3, but the first condition, all the faces are not congruent nor regular polygons. So this is not a regular polyhedron. Is this a regular polyhedron? All these are congruent, but this is not. Alright, suppose I take a double pyramid like this and all the faces are congruent now. Is it regular? Well, check the vertices. At this vertex we have 5 meeting here, we have 5 meeting here, but what about this? 1, 2, 3, 4. So this is not a regular polyhedron. Okay. Now, that means that if you want a regular polyhedron from this, we already have the vertices condition. If we make all the faces regular and congruent, it will become regular polyhedron. And what will it become? It will become a cube. Cube is just like a cuboid, except that all the faces are square faces and therefore they are congruent to each other and regular, and so this is a regular polyhedron. Okay? Now, about this, the problem here was not with the congruent faces but with the number of vertices. Now, at here we have 4 vertices meeting at every point, but here we have 5 and here we have 5. Now mind, instead of a pentagon, if we take a square, what will happen? We shall have only 4 vertical and 4 downwards, and 4 meeting here, 4 meeting here, 4 meeting everywhere. It will become a regular polyhedron and it will be exactly this. As you can see, in the middle there is a square where I am holding, and on this square we have a pyramid here and a pyramid here, and at every vertex there are 4 and all the faces are congruent. So that is a regular polyhedron. Now for the regular polyhedron, we will try to see the beauties of this regular polyhedra. First we look at the external one, and then we'll go over to the intrinsic, which is more important. The external property is that if you take any regular polyhedron like this and compare it with this, you look at it from anywhere, it will look the same. This will not look the same. Same thing here. Later on we'll see that this is a regular polyhedron. This also, keep it any way you like and you see the same because it is symmetrical. All the faces are congruent. Everywhere at every point there is symmetry and so on. And so they are very good looking because of their symmetry, or in other words, that is the external beauty, extrinsic beauty. What is the internal beauty? For the internal beauty, we have to do a little bit of knowing these models more. The first thing that we want to know is, what we want to observe is, that polygons can be had, regular polygons can be had for any number of n, but as we just mentioned, regular polyhedra may not be possible for every n. In fact, it has been proved that there are only 5 regular polyhedra. The smallest is this one. We call it small not by size but by the number of faces. This has 4 faces. It's a tetrahedron. This has 6 faces. There is none with 5 faces. Now 6 faces we normally call a cube. This we normally call a pyramid, but we shall call it a regular tetrahedron. This is a regular cube or a regular hexahedron. Hexa is 6. There are none for 7. For 8, you have what we call an octahedron. Octa is 8. 8 faces, and you will see that there are 8 faces and 4 meet at every point. Then this is 4 faces, 6 faces, 8 faces. The natural thing would be, alright, then maybe there is none for 9, but there must be for 10. No. None for 8, 9 or 10, and directly, or 11, and we have directly one with 12 faces. As you can see, that these 2 faces which I have under my finger, between my fingers, and each is a pentagon, and there are other pentagons on each side. So there are 5 of these pentagons. So the whole of the bottom is bottom plus 5. Similarly, top plus 5. So 6 and 6 is 12. So this has 12 faces. And of course, at every vertex, we have 3 pentagons meeting. Everywhere. And finally, after 12, there are none for 13, 14, all the way up to 19. And here is one with 20 faces. You can see that at this point there are 5 triangles. At this point also there are 5 triangles. So 5 at the top, 5 at the bottom. And in between you can see on each of the top one, you have one below, downwards, going downwards. And on each of the triangle below, there is one going upwards. So there are 5 downwards and 5 upwards, that means 10, 5 and 5, that makes 20. And we call it an icosahedron, means a solid with 20 faces. Well, okay. So that is the first beauty, intrinsic beauty, that there are only 5 such regular polyhedra. Alright, for the next thing, we need to work out a little bit. Let's see. What we normally do is, I write down the names of these, starting from the smallest, and I will not write regular everywhere. Tetrahedron, then what we call a cube is a hexahedron. Hexa is like hexagon, it is 6. Then octahedron, octa is 8, like octagon. Then this is 12, 10 plus 2. So it is do is 10 and deca is, do is 2 and deca is 10. So this is with 12 faces. And the last is icosahedron. Now tetrahedron, the usual custom is this. So I stick to it. Tetrahedron has 4 faces, hexahedron 6 faces, octahedron 8 faces, dodecahedron 12 faces, and this is 20 faces. Now, V stands for vertices and E stands for edges. Each one we shall calculate the vertex or count the vertices, 1 at the top and 3 at the bottom. See, there is a system in counting, so we don't forget. because we don't want to mark here on the model that this is what we have counted already. We don't want to repeat. So the tetrahedron has 4, and how many edges? 3 vertical and 3 at the bottom. 6. Okay. What about the hexahedron? Vertices 8 at the top, 8 at the bottom. I'm sorry, 4 at the top and 4 at the bottom. That makes it 8. Oh, and at the edges. 4 at the top, 4 at the bottom and 4 vertical. That makes it 12. Octahedron, 8 faces. How many vertices? 2 at the top and bottom and 4 in the middle. That makes it 6. And how many edges? Well, 4 at the top, 4 at the bottom and 4 in the middle. That makes it 12. Dodecahedron. Faces we have counted, vertices. There are 5 at the top here. Similarly 5 at the bottom. So between my near my fingers I have 5 here and 5 here. And in between, opposite each top one I have 1. Opposite each bottom one I have 1. That means I have 5 downwards, 5 upwards. So 10 more and 10 these. So I have 10. This is equal. So this is 20. 5, 5 and 10. Oh, and edges. Now edges we can count, of course, exactly like this. But there is an easier way of counting the edges. We know that it has 12 faces. And each face has 5 edges. So we have 12 into 5 is 60. But each edge is counted in 2 faces. This in these 2, this in these 2 and so on. That means it is 60 divided by 2 and that makes it 30. Okay, and the last one. We want the vertices, 1 at the top, 1 at the bottom. Then you can see this is the top. And there are 5 going from here, triangles, and they have 5 vertices here. So 1 top, 1 bottom, 5 here and similarly 5 here. So 10, 11 and 12. And what about the edges? Well, we know that there are 20 faces. Each is a triangle, so 3 edges. 20 into 3 is 60, but each is considered twice, so half of it, and that is 30. Okay, so the counting part is over, and now some observations. Do you observe that this is 12 and this is 12? Similarly, this is 30 and this is 30. But that's not enough. You can see that this has 8 vertices, this has 8 faces. This has 6 faces, this has 6 vertices. So they are related in cross. Same thing here. Vertices and faces are the same. Here the vertices and the faces are the same. And here it's just both are same. Well, look, now the first observation, the first point of beauty was that there are exactly 5. The second observation now is a more general one, and it does not relate to only regular tetrahedra, and that is what you know already, Euler's result for any polyhedra, and that is what will happen here because we are going to take V plus F minus E. How much is that? V plus F minus E. So 8 plus 6 is 14 minus 2. This will minus 12 will be 2. 6 plus 8 is 14 minus 12. It has to be the same. Because this is same and this sum is same. Similarly here, 32 minus 30. And similarly here, 32 minus 30. And here, 8 minus 6. So what is the result? The result is that V plus F minus E. This is the observation. We have not proved it. And this is true for any polyhedron. And because these are also polyhedron, it is true for regular polyhedra also. Alright, this is called Euler's result. This is Euler's result. V plus F minus E is equal to 2. Now, the second and more beautiful thing is that that comes from this observation. Look at the hexahedron. Here is the hexahedron. It has 6 faces. So if in each face I take a point and join them, I will have a polyhedron with 6 vertices. And 6 vertices is this. And if I take the centers everywhere, it will be regular also. So if I take the centers of the cube, faces of the cube, I will get a 6-sided or with 6-sided polyhedron. 6 vertices. The polyhedron will 6 vertices. And let us see how many sides. It's right here. Here is the cube or the hexahedron. Everywhere we have taken the center, as you can see, and joined them. And what do we get? A regular polyhedra with 6 vertices, which is precisely the octahedron, as you can see. And then we would expect that the same thing should happen the other way. Yes, it does. Here is the octahedron. It has 8 faces, so you get 8 points when you take the centers. And when you get 8 points, you have a hexahedron, because you have 8 vertices here. So hexahedron is a cube, and as you can see that inside the octahedron you can inscribe a cube. And inside a cube you can inscribe an octahedron. These are called duals of each other. One can be inscribed in the other, and if you keep continuing inside the cube tetrahedron, again inside the tetrahedron cube, inside that a tetrahedron, and so on. If it is possible, we can try that. Okay, now that means, does that happen for these two also? Let us see. Let's take a dodecahedron. 12 sides, so we'll get 12 vertices. It's right here. Here is a dodecahedron. It has 12 sides, so when you take the centers, you have 12 vertices, and when you join them, you can see that here is a pentagonal cap, sort of, or a pentagonal cap, and you have an icosahedron inside the dodecahedron, and the other way around. When you take an icosahedron, you have 20 centers, so you have 20 vertices, and 20 vertices is dodecahedron, and you can see that inside this you have a dodecahedron, which is precisely this. So, well, what about the tetrahedron? There were 5 regular polyhedra. They found out their pairs or their friends. These two are friends, these two are friends. Nobody to take the tetrahedron, but the tetrahedron, although the smallest, is very strong enough. It says, I don't care for others, I am my own friend. Because, as you can see, it has 4 faces, and when you take the vertices, centers, you take 4 vertices, so it is a tetrahedron. So a tetrahedron can be inscribed in a tetrahedron. Inside that tetrahedron you can get another one and so on. So these two are duals, the cube and octahedron. These two are duals, dodecahedron and icosahedron. And a tetrahedron is called self-dual. It is its own dual. Well, okay, that teaches us not to bother about what others do. Take care of yourself by yourself. Well, okay, so now you can see that this is the second beauty. The mathematical beauty is that they can be meshed like this 2 by 2, and the centers of one give you the other one when you take pairs, or they can be inscribed in each other. One in the other in the first, and so on. Two such pairs, and the fifth one is self-dual. And the models by themselves also, they look nice. So they are beautiful. That way also, if you are keen on mentioning it. Well, okay. So that's the Platonic solids. And they are called Platonic because most people interested in mathematics are very much interested in Platonic solids, even though they are not included anywhere in their course, either school or afterwards. Simply because of its beauty, it has fascinated so many, and especially Plato was just crazy, and he associated the 5 elements with these 5 polyhedra, and therefore in his honor they have been given the names of Platonic solids. Okay, thank you.